Okay, let's slow things down a bit going into I, which I guess I would call the hardest balance on the sheet. In I have H, SiCl3 reacting with a bunch of water and forming two products. One of them an absolute beast, H10, Si10, O15, and the other one, much nicer, HCl. Okay, how could we ever even think about starting to approach this? Well, you know what? I'm going to assume that I don't have some sort of giant number in front of this giant molecule. If this is 7, I'm just never, ever, ever going to figure that out. So let's just kind of be easy on ourselves and do some guessing testing with some small numbers here. In fact, let's try the smallest number there is, 1. I'm going to see that that does, in fact, pale. Usually, if you've got a giant guy like this, you're only going to need 1 or 2 of them to make the reaction balance. So starting with 1, just checking to see what that works out to, is not a terrible idea. If I have that 1, that tells me something about my silicon. It tells me I only have 10 silicon. And it tells me something about my oxygen. It tells me I have 15 oxygen. So right away, I can put a 10 here for 10 silicon. And I can put a 15 here for 15 oxygen. Now, if I have 10 here, then that's 10 groups of 3 chlorine, which is a total of 30 chlorine. And I can finish up with the 30 chlorine here. The only thing left to do is to kind of check my work, because while I've done silicon and oxygen and chlorine in a way that I was kind of free to, I still don't know for sure about hydrogens. So let's check my hydrogens. Here I've got 10 hydrogen. And here I've got 15 groups of 2 hydrogens per water molecule. 15 times 2 is 30. So I've got 30 hydrogens, meaning there are 40 hydrogen atoms involved altogether in my reactants. Over here, I've got one group of 10 hydrogens. And then I've got 30 hydrogens here to work out one more time to 40 hydrogens among my products. So actually this works. I am balanced. 10, 15, 1, 30 as my coefficients are the things that I was looking for. If you got that one, you can do this. You are good to go. Jay gave us, oh, let me do a new slide. C7H9 plus HNO3 in a reaction that gave us C7 H6 NO2 3 plus H2O. This is what we call a redox reaction. It means that there was active stealing of electrons going on while the reaction happened. And that makes things really tough. It makes it really tough because normally we can treat something like an NO3 ion as, you know, its own individual unit throughout the whole reaction. But here, my NO3 actually changes to an NO2, which is a major pain in the butt. We need to study these sorts of redox reactions because they're very important in terms of generating electrical power or building batteries and stuff like that. But they are pretty darn annoying to balance. In grade 12, we actually go over some strategies to balance these guys kind of piece by piece that would be somewhat useful for us here. But I'm going to bury that lead and instead solve this guy the good old-fashioned way. It's actually really not that bad. What I need to do is triple up here. Is that right? Triple up or double up? Yeah, triple up here. And then triple up at the end here too. And if we work through, we're going to see that that actually gives us what we need. It gives us 7 carbons on this side and 7 carbons on this side for free. If we want to count our nitrogens, then I've got 3 nitrogens on this side. And then I've got 3 nitrogens, because I'm getting 1 for each of those nitrite ions. So 3 nitrogens on this side. Yeah, that means that I have to think about the individual atoms inside of my brackets, and that's what's so annoying about this redox thing, but that's how it works. Each of these nitrates has a single nitrogen. I've got 3 of the nitrates, so I've got 3 nitrogens. If that threw you for a loop, I don't blame you. We didn't really talk a ton about that, and it hardly ever comes up, but in these redox reactions it does. All right, I have 3 groups of 3 oxygen, so a total of 9 oxygen on this side. And then I've got 3 groups of 2 oxygen, so 6 oxygen, plus 3 oxygen, so 9 oxygen on this side. Again, that meant I had to kind of work inside my brackets there. Super annoying, but it happens. And we ended up with a balance. Finally, for my hydrogens, 9 hydrogens here, and 3 groups of hydrogen here. Gives me a total of 12 hydrogen. And then 6 hydrogen here, and 3 groups of 2 hydrogen here. Gives me a total of 12 hydrogen. So that is the balance for this one. I think I might almost consider this guy a trick question, given how little we talked about dealing with these sorts of brackets. And like I said, there are tricks for this sort of reaction that you will learn later on. But if you got this one, that's awesome. Last guy is K. And this one looks like a big nasty mess, but you might have imagined that as we were wrapping up the sheet, I was being somewhat nice to you, and certainly I was. This guy just looks mean, he's really not. So I've got some sort of carbohydrate here. This is probably some sort of biological molecule, like a sugar or an alcohol or something, reacting with sodium hydride and hydrochloric acid, HCl, and I'm producing C5H12O2 and salt, NaCl. The balance is just this. What I needed to look at was the fact that my carbon stayed the same. My oxygen stayed the same. So all I really needed to do was go from 8 to 12 hydrogens, which means I needed to add 4 hydrogens. 2 groups of 2 hydrogen here, plus 2 groups of 2 hydrogen here are the 4 hydrogen I needed to add, and then 2 sodiums and 2 chlorines give me 2 sodium chloride. So kind of a cheeky one at the end there, where the numbers were a lot smaller, and although it looked like a beast, it really wasn't. Okay, we made it through. Thanks for tuning in. Hopefully, after all of this, you can go into the next set of questions we'll look at, ready to tackle them. I promise that I won't put another redox one on there. I only realized, as I was recording afterwards, that one was kind of mean. But if you got question J there, then that's awesome. Thanks for watching, guys.